to 12, around 50 minutes or
Oh,
please,
I will.
please,
Yeah, don't worry. I project over here. Take off.
ꯑꯗꯨꯝ ꯀꯩ ꯇꯧꯕꯤꯔꯣ ꯑꯩ ꯁꯥꯏꯖꯁꯦ
Oh, I don't
ꯁꯥꯏꯖꯁꯦ ꯈꯤꯇꯪ
know.
ꯅꯠꯇꯕꯅꯤꯅ
Oh,
ꯑꯗꯨꯝ
I
ꯁꯦꯂꯦꯛ
do
ꯇꯧꯔꯒ
the. I do the kind of do yeah. Oh, oh, yeah, yeah. Yeah. 오늘 이도 수야하잖아. 뭐 공주 하나. 어? yani dum
ꯊꯣꯛꯂꯛꯀꯦ
pare kena tahu saya sudah mah apa nih
ꯁꯤꯒꯤꯗꯪꯒꯤ ꯑꯣꯏꯕ ꯃꯥꯏ ꯁ꯭ꯇ꯭ꯔꯤꯝꯗꯪꯒꯤ ꯑꯣꯏꯕ
oh mai segitu ya
ꯁꯥꯏꯖꯁꯦ ꯈꯤꯇꯪ ꯁꯦꯝꯗꯣꯛ ꯁꯦꯝꯖꯤꯟ ꯇꯧꯕ ꯌꯥꯔꯣꯏꯕ
ah
ꯄꯤꯛꯄꯅꯤꯅ ꯈꯤꯇꯪ ꯁꯥꯏꯖꯁꯦ
oh
ꯄꯤꯛꯊꯣꯛ ꯁꯦꯝꯖꯤꯟ ꯈꯔ ꯇꯧꯕ
ada kagak tahu ya
ꯑꯩ ꯇꯧꯕꯤꯔꯦ
friends oh okay I think we are all already in the entangled state in the morning session in our session and Professor Burma has given a very exhaustive presentation the the quantum science and particularly the recent developments of quantum technology, right? And there he mentioned, entanglement, quantum entanglement. Please be seated. In my talk, I will be at the A stage of the ABC of the quantum theory, quantum mechanics. So I think you have come down to your state of quantum entanglement, and you come down to the initial level, and I will just review, keep it, how quantum mechanics was developed. Keep the story of this. This is just a beginner's approach, and it is pedagogical introduction to formulation of quantum mechanics. What I am going to speak is just very simple things, or just how the idea of quantum was developed and how quantum mechanics was formulated, mainly for the beginners. I'll start with the deficiency of classical mechanics, classical theory. In classical theory of the black body radiation spectrum, about the deficiency, how classical theory failed to explain the black body radiation spectrum. And see, I will write an expression here. Classical Rayleigh's law Rayleigh's law said the black body given like this. U nu is equal to, I don't know whether it will be visible for you, nu square. That is, nu is the frequency of the radiation. So the U nu is the energy density. U nu d nu is the energy of the radiation lying between frequency nu and d nu. And so this expression says that the energy density will diverge like the square of the frequency. That means as the frequency can be very large, right from 0 to infinity. So that this is a problem, which is not physical thing. This is not what is observed actually. For this divergence with the square of the frequency was known as this quadratic divergence was known as the ultraviolet catastrophe that time. To resolve this, and which is, certainly it is not physical, because spectrum cannot go to infinity. Right? To remove this deficiency of the blackbody radiation, to explain this blackbody radiation spectrum, Planck in 1900, Max Planck in 1901 introduced the hypothesis that in thermal equilibrium, the exchange of energy, that is, exchange of energy between radiation and matter, between matter and radiation of frequency nu, takes place in quanta in discrete quanta. I'll explain later. The exchange of energy between radiation and matter means absorption or emission of radiation of frequency nu takes place in quanta of energy is nu. That is, it doesn't, he did not outright say that radiation consists of quanta of energy. He said that the exchange takes place in quanta, in discrete manner, in this thing. And this was Planck's hypothesis. And with this introduction of this hypothesis, and he derived his famous formula, that the formula is simply, this gets a multiplication factor is nu by kT, power nu by kT minus 1. And so this exponential, this introduces the conversion factor actually. So the radiation spectrum looks like first quadratically rising, then falling exponential decay. So classical mechanics, classical theory, not mechanics, classical thermodynamics gave Rayleigh's law, which makes this nu square divergence. And then Planck's hypothesis, with the Planck hypothesis, Planck formula calls that this comes to a maximum, then also this. And this adequately explained, this was enough to explain the observed blackbody radiation spectrum. Yeah. Then in 1905, Einstein again extended this Planck's idea by saying that not only in the exchange, but radiation itself consists of quantum or quanta of energy. Radiation of frequency nu consists of quanta. You can think of as particles of energy is carrying energy as nu, and a momentum E by c. That is h by lambda. This is the famous connection between the wavelength and the momentum, which we shall come later also. So the process takes place. This is the probability of finding the particle, locating the particle, or the particle being at the position R within the volume element, the V at particle R. This is equal to probability of finding the particle at R. What is again within the volume element dV at the position R. although I have no intention to go into probability interpretation, why I am giving this is that this interpretation requires that this psi, wave function psi, be square integrable. That means this integral should exist. It's not diverse. And this requirement that psi should be square integrable led to the quantizational energy for bound systems. This is how quantizational energy manifests itself in the Schrodinger's approach. That is by interpreting psi square is the probability amplitude, and interpreting mod psi square is the probability probability density. Right. This requires that this psi should be square integrable for bound systems, and this leads to the quantization of energy in this. And the atom, you can solve this equation for the hydrogen atom and calculate the energy levels. Energy levels which you obtain there is exactly the same as what Bohr earlier, solving any Schrodinger equation. To the formal quantum theory. In this narrative of Schrodinger formulation of quantum mechanics, idea of representing dynamical variables in momentum by differential operator is only implicit. It is not explicitly built in the theory. But in Heisenberg's formulation of quantum mechanics, idea of representing dynamical variable by matrix operator is explicit. Heisenberg explicitly introduced this idea of representing dynamical variables by operators. Frankly speaking, I never understood how Heisenberg formulated this matrix mechanics. I tried to understand from some articles, this thing, and the books, but I never found a satisfactory answer there. Heisenberg was actually studying the transition probabilities to explain intensities of these spectral transitions, helium atom or something like that. And later on, what he found was matrix mechanics. It was shown by Born and Jordan. And here I quote Professor Mukunda. He said, Heisenberg, Born and Jordan had shown that Bohr quantization rules of all quantum led to the statement that position and momentum variables of quantum system obey commutation relation of the form. That the position, the Q, IQ, they commute, and momentum variables, they commute, but the position and momentum, they do not commute. In other words, this is equal to this Qj pk minus pk Qj isk delta jk. And the reason why I mention here is that I never knew how Heisenberg arrived at these commutation relations. In fact, at the same time, Professor Mukunda also says that coming to formulation of mechanics theory, we make the following observations. Heisenberg's original version of quantum mechanics brought the idea of dynamical variables becoming operators, but it did not especially bring in the concept of state of motion of a quantum system. Quantum system की state idea this idea though was not there in Heisenberg's formulation of matrix mechanics. But in the Schrodinger's approach, in the wave mechanics, the idea of operating idea of representing dynamic variables by operators is not there, but the concept of state of the physical system was there in the Schrodinger version of quantum mechanics introduced general concept of state of a dynamical system. Now, having noted these things, the idea of representing dynamical variables by observations from the Heisenberg approach, the idea of representing dynamical variables by operators from the Heisenberg's formulation, and the idea of the state of a system, physical system, from the Schrodinger's approach, Schrodinger's method, we are now ready to formally formulate quantum mechanics. Quantum mechanics is formally formulated in a linear vector space. We cannot avoid this language of the vector space. And now I come to the basic postulates of quantum mechanics. Right. Oh. There are at least 5 basic postulates. First is state vector. The state of a physical system is represented by a vector in a linear vector space. Dynamical variable. A dynamical variable is represented by a Hermitian operator in the space S. So the postulates. This is the origin of many of the parameters. This expansion postulate. Expansion postulate is a Hermitian operator dynamical variable is a complete set of eigenvectors. Short term such as operator is observable. Short term is such an Hermitian operator having a complete set of eigenvectors is given another name observable. Right. Hence, an arbitrary state vector can be expanded as a linear combination of this is what is generally called the expansion postulate. Right. And result of measurement. The result of a single measurement of dynamical variable is one of the eigenvalues of the operator representing the dynamical. Suppose you are imaging momentum, then the result of a single measurement on a system is one of the eigenvalues of this momentum. Right. That is the idea. If you are going to observe a dynamical variable on a system, then whatever be the system, you are making the measurement of that. The result of your measurement of that variable is one of the eigenvalues of this operator. Right. And then comes the fundamental commutation relation. The pair of classical canonically conjugate variables Q and P become Hermitian operators obeying the commutation relation QP is equal to I scat, where IQ is the position back operator and P is the momentum operator. And this is fundamental commutation relation is generally put as one of the fundamental postulates while formulating quantum mechanics. That is why we are giving here. For systems having more than 1 degree of freedom, the postulated fundamental commutation relation will read like this. This is position and momentum, then they may not commute, and position and position commute, momentum and momentum commute. Okay, next. So with these 5 postulates in mind, we formulate the quantum mechanics, formally formulate the quantum mechanics. Now in the formulation, I showing the picture of quantum dynamics. In this picture, you can view the dynamical variables not evolving in time, but the state vectors are evolving in time, but not the dynamical variable. State vectors evolve dynamically. It's not some explicit time dependence. As the dynamics of the system evolves. That is represented by state vectors evolving dynamically while operators, that is dynamic variable, remain stationary. We postulate existence of a temporal development operator or evolution operator, T0. So this is temporal development operator. It is such that when it acts on the vector, state vector at time t0, t0, that gives this psi t. Oh, it is okay. Good. So this operator has to be unitary. Then we can show it, right? Suppose I is the Hamilton generator of t0, defined by the Hamilton operator is introduced in this way that time development for infinitesimal time interval t to t plus delta t. For this, when this operator is the unit operator plus delta t equation. This is masla I square d dt by dt t is t0. Acting on psi t0, we get the equation I square d psi by dt is equal to I psi. This, if we identify ice with the Hamiltonian of the system, then we get the familiar Schrodinger equation. So in briefly, there is this in the Schrodinger picture, the wave function psi naught, psi t naught, develops into in time t into psi t, which is obtained from psi t naught by this time development operator t0. But the operator a dynamic variable a remains the same at this thing. This is the Schrodinger picture, right? Then comes to Heisenberg picture. From here, from the Schrodinger to obtain the Heisenberg picture through unitary transformation by the unitary operator ut0, which is just nothing but the inverse of t0, which is also equal to t to t0 vector. And then the state vector phi psi changes to phi, transform to psi. That is, it is psi t0. That means whatever this thing, it transform back, whatever the time t, this transformation will take back the psi t to psi 0. That means psi does not dynamically evolve. But then operator A transform this A to this omega, this is U dagger or U inverse. That is similarity transformation. And obtain the Heisenberg equation of motion, I squared d omega by dt is I omega. This is the famous Heisenberg equation of motion, right? It is quite simple to deduce these things. Okay. Then, okay. बताइए बोले Okay. Well, this is roughly the idea that in the quantum mechanics is formulated in a linear vector space, which is generally called Hilbert space. And in this Hilbert space, we develop two pictures. One is Schrodinger picture, in which is the Heisenberg picture. Yes, the state vector representing the state of a physical system do not evolve in time. It remains stationary. Whereas the dynamical variables evolve in time according to an equation which is known as the Heisenberg equation of motion. As I said, I never knew how the 자이게 지마망다 지마망다 마망다 마다 하이갈라 좀 징가봐 say postulate operator says okay no 어저께도 야래 지갑해요 yeah this canonical commutation relations I never knew how this was deduced by Heisenberg but only place where this equation was some sort of deduced was in the textbook by Paul Dirac. In his book, he beautifully observed the classical Poisson bracket relations, and from there he could deduce these fundamental commutation relations. Looking, it is a little bit, when I say that, the fundamental commutation relations were derived from classical Poisson bracket relation. What I mean is that he put an idea. He could by ingenious who is looking at the this by critical loop, by involving the classical equation of motion in terms of Poisson bracket, involving that also he could arrive at this commutation relation. That is what I mean. It is not that he deduced, it is not that Dirac deduced this quantization conditions from classical mechanics. It means that he took the analogy with the classical Poisson bracket description of classical mechanics, right? And he arrived at this. And I think I will better conclude. Finally, I want to come to about the angular momentum and its spin. Simatanda. Last. Simatanda. Last. Angular momentum. Conventionally and also practically, angular momentum is introduced while solving the equation for particle in a central potential through the technique of separation in spherical polar coordinates. In this approach, discrete eigenvalues introduced in the equation, discrete eigenvalues of the z component, the z square, which is defined as the z1 square plus z2 square plus z3 square. And this operator has eigenvalues, some z plus 1. Of course, this I-squared square, so forget about this thing. And this is the eigenvalues of this, where z is a number where twice z is an integer. In other words, z is integer, z can be integer or half integer. That is, that half integral values of z will emerge in this algebraic way of algebraic approach towards angular momentum. That is what I mean. And in the Schrodinger approach, only the integral values of this angular momentum z square will emerge while trying to solve the Schrodinger equation for a centrally symmetric, for a central potential right? But not half integral values will emerge. So this algebraic approach will lead also to the half integral eigenvalues, right? So the appearance of this half integral I will consider is a manifestation of the idea of intrinsic spin. So in the Schrodinger approach, it is difficult to introduce the, the, the idea of spin. But in this algebraic approach, the spin still arises automatically on its own. Well, I think I have taken enough time. I am very floppy, because I am used to classroom lecturing with with blackboards or whiteboards.
I think this is very thought-provoking. So many things we bypass ourselves without thinking much. Okay, Sir has given the emphasis on subtleties you can call about. In fact, this thing we didn't think about much about it, even though we think it is real algebra like that. But still, we can discuss later on. But as a student, still I have many doubt in many things in quantum mechanics. Number one, when I feel that d by dt side, Sir told that it is in order to have a sinusoidal wave function or evolution, d by dt, linear in time.
I don't know.
I want to give another reason that in order to make rho positive, you require first order in time derivation. Okay. In order to make rho positive, you require first order. It is second order, you will get plus minus. Okay, that I want to get. Another one which we find difficulty is that even though everything others dynamical variables are operator, time is not operator.
Yes, right.
Time is still a parameter in quantum mechanics. So this is why in quantum mechanics, in special theory of relativity, time and space are in equal
Treated on the
footing.
same footing.
But here in quantum mechanics, they are
Yes,
opposed.
yes. You are right.
Space is operator, time is still parameter. So it will create problem. These will be solved in quantum field theory again. Never mind. But again, this is why in canonically conjugate pair, X and P, we have the commutation relation Sir has given. X and P commutation equal to I square. But when there is no commutation relation between E and T, because T is the parameter. Be careful about it. Some textbook wrongly written this thing. There is no commutation relation between E and T, even though they are canonically conjugate variables. Because T is the parameter, not operator. But still they have uncertainty principle. It is my observation. I don't know, it may be wrong. Okay, thank you, sir, very much. And if you want Sir's thing, either you give your email address to me or you can get from here. Or if you give your email address, I can send you to your email address.
Okay, thank you. I think
Okay, thank you.
we are heading towards an.
Kailan mo pini hay Peter bo no? Tayo budol pini.
I parting statement untuk bicara. We are heading towards the era of say this quantum technology, where you have quantum computers, entanglements, quantum computers, and quantum processors, and artificial intelligence, and so on. In this, talking about this quantum entanglement, Bohr and Einstein is the 1927 Soleil conference in this thing. Bohr and Einstein are always entangled. Or they are opposite to each other. So one day, some Miss Spooky is a name. Because I use this name Spooky because Einstein called action at a spooky action at a distance, this entanglement. Right. So one Miss Spooky wanted to find out whether Einstein is alive, still alive or not. So she went to Copenhagen and found Niels Bohr not alive, dead. He found it must be after 1962 or something. So Miss Spooky found Bohr dead, alive. So she immediately inferred that Einstein should be alive. Because the two are oppositely entangled. But by the time Bohr dead, Einstein was also dead. And so be careful of this quantum entanglement. It is such epistemological discussions are, carries you, so far that you go thoroughly confused and you try to come back from that confusion and become a normal student. Thank you.
One point I want to also add here is that what Char is telling that commutation relation Q and P, the origin which Heisenberg first or Dirac first was not knowing, and so there is a story that Dirac used to go on Saturday a long distance in the morning alone. He is not going along with other people. He is going long distance on Saturday, sometimes climbing hills and all that. It is his habit. While going, he used to think about physics. So one day when he was going, he started thinking about if it is like this, it will solve the problem. Then it is similar to Poisson's bracket in classical mechanics. Only is the correspondence from Poisson bracket correspond to in classical mechanics. There is no Poisson bracket in quantum mechanics. Poisson bracket in classical mechanics, the corresponding would be commutation relation in classical mechanics divided by IIC. So that if this is the thing, it will work. So it came to his mind, but he forgot what is exactly Poisson's bracket. He just remembered. So he could not resist to see what is exact form of Poisson's bracket. But on that day it was Saturday and the next day is Sunday. He could not sleep 2 nights. Okay. On Monday morning, he rushed to the library. He was the first person to reach the library, and he searched a book, mathematics book he learned when he was a student, and he found out the Poisson's bracket expression. And so, in that way, I think the credit should give to Dirac, not Heisenberg. Sir, this is the goal, and we'll present.
Oh, thank you. Sorry. Thank you.
Dạ, phải hồ rồi. Dạ, phải
Yan,
cái
yan.
này. Ô, dạ, cái này.
Yan.
Ông cứ nhìn video. Thank you, sir.
Thank you.
Next is respected Ado aina financial constraints dagi mayam di yen bom nam hugdo bagi ado email pipira dagi on dagi tum logi IYQ zari ngam video si on quantum entanglement that's in a particularly Bohr Einstein debate paradox. Thank you.
$35 minutes, right? So I shall try to finish my talk within this 35 minutes. When Nimai came to me and requested me to turn quantum entanglement, I told him, "Oh, Nimai, I am not an expert in this field. I have not published any paper in this." And even then he said that, "Please talk something on this." Because after my retirement in 2017, just to pass time, I started reading on this quantum entanglement. So what I'm going to do today is to share with you some of the things I learned from my readings. And again, I am no expert in this field. It is a very slippery ground to walk on also. In 1935, Einstein, Podolsky, and Rosen published a paper in Physical Review. And the title of the paper is, Can Quantum Mechanical Descriptions of Physical Reality be Considered Complete? Let me read again. Can quantum mechanical descriptions of physical reality be considered complete? This is the title of their paper. The idea was given by Einstein. The mathematical calculations were done by Rosen, and the writing part was done by Podolsky. In fact, when the paper was published, Einstein was not happy because it was written in a very abstruse way. He thought it could be written simpler. Anyway, here, please mark these two words, these three words, physical reality and complete. I shall come to that later on. And as it was the custom of Physical Review, the paper was sent to some reviewers for review. And on learning that his paper was sent for review, Einstein was very annoyed. And after that, he never sent any paper to Physical Review. Anyway, so he was never sent any paper to the Physical Review after that. And Schrodinger read the paper with great interest. And he wrote a letter to Einstein. And in that letter, he introduced a word in German. And I cannot pronounce it even though I cannot pronounce it, I shall read it out. The word was Beschränkung, which he himself later translated into English as entanglement. And you know, Schrodinger speaks English as his second mother tongue because he learned this language from his maternal grandmother, who was English from a very young age, early age. So he speaks English just like German, as fluently as German. And in this letter, and he used this word entanglement to describe this word entanglement. In this letter, he used this word to describe the correlations between two particles that interacted and then separated. Then in another paper published shortly after the letter, he explained further. Any entanglement of predictions that take place can obviously only go back to the fact that the two bodies at some earlier time form, in a true sense, one system. That is, were interacting and have left behind traces in each other. Interacting, separated, but left traces in each other. So he described entanglement in these words. He explained further. If two separated bodies, each by itself non-maximally, enter a situation in which they influence each other, and then separate again, then there occurs regularly which I have just called entanglement of our knowledge of the two bodies. In simple terms, entanglement is a phenomenon in which two particles remain inexorably linked or correlated no matter how far they are apart. So interact together, separated, they went farther away, but they remain correlated. This is the meaning of entanglement Schrodinger used in his paper. I shall now discuss briefly the EPR paper, which gives birth to this concept of entanglement. We are not certain if Einstein was aware of this concept, because in his paper we don't find any of this word. We do not find this word. The sole objective of Einstein's paper and EPR's paper was to show that quantum mechanics is incomplete. Now, mark these two words, physical reality and complete. And what are the meaning of these terms? What do you mean by physical reality? And Einstein, I should not use this word, Einstein was aware of the difficulty of defining what reality is, because it is a very slippery ground. In philosophy, so many philosophers, great philosophers discuss on this problem, and there was no agreement. So many views. And we don't know which one of the views is correct. So it is a very slippery ground. So instead of defining what he has done in his paper is, instead of defining what reality is, he gave a criterion. And and using these meanings, he tried to show that quantum mechanics is incomplete. So now I shall explain briefly the EPR experiment paper. And very briefly, I shall take only the main part, explain only the main parts. The EPR experiment is something like this. A source, if there is a source, it emits two particles in opposite direction. And there is a detector A, it may be an experimenter called Alice. Here A, another particle goes in the opposite direction. Here is another detector V, and we call it Bob. Alice is here, Bob is here. So it emits two particles in opposite directions, A and V. And the brief interaction between the two particles provides, there is a brief interaction here, and this brief interaction provides the sheet of entanglement between the two particles. So now quantum mechanics forbids the exact simultaneous measurement of the position and momentum of either particle. But quantum mechanics does not provide the exact simultaneous measurement of momentum and the relative distance between the two particles. So what he did was, he measured the momentum of the particle A coming towards Alice. Let us call Alice. Let us call his particle A. So he measured the momentum of the particle A. And since the two particles interact briefly, momentum is conserved. So knowing and measuring the position, the momentum of particle A, and using the conservation of momentum, the momentum of particle B is determined, is known. And secondly, we know the relative distance separation between the two particles. So knowing the position of particle A, the position of particle B is also known. Therefore, knowing the position and momentum of particle A, the position and momentum of particle B is known. And therefore, momentum of the particle B and its position can be known. Now, this is a very nice trick. He avoids the simultaneous measurement of the position and momentum of particle B. He avoids that. So, by so EPR avoided the direct measurement of the position and momentum of the particle B, thus bypassing Heisenberg uncertainty principle. So this is a very nice trick. And Einstein, now let us come to the meaning of this physical reality. This is the result of his experiment. Of course, this is a hypothetical experiment. Now, from this measurement, he will come to the conclusion that quantum mechanics is incomplete. How is that? Any serious physical theory must take into account the distinction between objective reality, which is independent of any theory. Objective reality is independent of any theory. And the physical concepts with which the theory operates. There is a physical reality, and the concept of this physical reality with which we work in physics. So there is a distinction. We must be aware of the distinction between these two operates. These concepts are intended to correspond with the objective reality. The concept we use in our physics, in our physical theory, must correspond to the objective reality. We try to conceive or understand the objective reality. And Einstein believed that objective reality lies beyond the physical theory. And beyond any theory, this view is very similar. His view of physical theory is very similar to that of Pierre Duhem. Pierre Duhem was a celebrated French historian of science and philosopher of science. And according to Duhem, under the sensible appearances, are revealed in our perception, there is a reality distinct from these appearances. We measure something, and that is not the reality, but the reality lies beyond that measurement. This is his view, Pierre Duhem's view. And to him, the resolution of these questions, does there exist a material reality distinct from sensible appearances? Or what is the nature of this reality? Does not lie with physics. Because this answer of this question lies in the domain of metaphysics. Anyway, but to Einstein, what we call science has the sole purpose of determining what is. The sole purpose of science is to determine, to understand what is. That means what is reality. The sole purpose of science is to understand reality. It is basics for physics that one assumes a real world existing independently from any act of perception. Objective reality exists independent of any observation. But this we do not know. That means this objective reality we do not know. Although it exists independent of any observation. So this is the philosophy behind his paper. And maybe with this philosophic perception in mind, EPR assumes that any complete physical theory must have a counterpart in it of every element of the physical theory. So any complete physical theory must have a counterpart of objective reality in its theory. Suppose there is a physical reality, and this physical reality has a counterpart in any physical theory so that the physical theory is complete. So this is the meaning of his of the term complete. Then what is the meaning of the reality, physical reality he used in his paper, the title of the paper? Therefore, defining reality is difficult and very slippery also. And you are bound to err. There is always element of error when you define reality. And therefore, instead of defining what reality is, Einstein laid down a criterion which he assumed to be sufficient and necessary. A criterion sufficient, we assume to be sufficient and necessary. And this is like this. If without in any way disturbing a system, we can predict with certainty, that is with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. So in the theory, you predict the value of a physical quantity with certainty. In doing that, you don't disturb the system, then there is an element of physical reality corresponding to that physical quantity. And it is very philosophical, so, but he avoids, again, defining what reality is. So this is his criteria of a physical quantity to be a counterpart of the actual physical reality. So in their hypothetical experiment, EPR predicted the exact values of the momentum and the position of the particle B at a given instance without disturbing B. So according to our criterion, the position and momentum of particle B are elements of reality, the counterpart of which must occur in quantum mechanics in order that quantum mechanics be complete. Momentum and the position are elements of physical reality. In order that quantum mechanics is complete, there must be counterparts of position and momentum in quantum mechanics. But quantum mechanics does not accept, because the exact values of the position and momentum at any given instant of a particle cannot be known because of the Heisenberg uncertainty principle. Therefore, quantum mechanics, they conclude, is incomplete. So this is their argument brief. And you must read the paper, but it is written in a very abstract manner. But idea is not very difficult. Okay? So my point is, we are dealing with reality and we don't know what reality is. So instead of defining reality, what Einstein EPR did was to give a criterion for a sufficient and necessary for a physical quantity to be an element of reality. Okay. So quantum mechanics, therefore, does not satisfy their criterion of completeness, and therefore Einstein, Podolsky, and Rosen conclude that quantum mechanics is incomplete. It is something like this, but this is not actually correct. So you are living here for many years. You have become a citizen of this country, and you went to cast your vote in an assembly election, and you are not allowed to cast your vote on the plea that your name is not in the voter list. So simply, the voter list is incomplete. So this is more like their argument. So now, central to the EPR argument, there is an assumption. And the assumption is called the principle of locality. This principle encodes a belief that whatever happens at A cannot have any effect on whatever goes on at B, or vice versa. So this is the principle of locality. This means that measurement of position and momentum of particle at A will have no effect on the measurement of position and momentum of the particle at B because of the locality principle. Combining this with the assumption that there is a physical reality independent of observation, we may say that the world is locally real. The moon exists even when you do not look at it. This is their position. Moon exists independently of any position. And why is it so? Because they have given this argument. So to them, the world is locally real. Real means we exist independent of any observation. Local means the locality principle holds good. Okay? So the world is locally real, according to Einstein. Okay. Bohr disagrees. Bohr are there? They are there. And to them and their group, in Copenhagen interpretation, I visited recently Copenhagen. I visited also Bohr Institute of Physics. And he has a very small room. And most probably that is the place where discussions, so many discussions with Pauli, Heisenberg, Jordan, Bohr must have taken place in that room. And most probably in that room, Copenhagen interpretation of quantum mechanics must be done. Very small room, anyway. And Bohr disagrees. He says that in the absence of any precise measurement of the position of an electron, for example, electron has no position. And in philosophy of science, this view is called anti-realist, or we call it instrumentalism. Okay? Has no position. And Bohr also counters, very beautiful, his argument against EPR, his defense against EPR here is very beautiful, to me at least. Here he counters never so succinctly that the pair of particles were entangled and form a single system, no matter how far apart they were. Therefore, if you measured one, you also measure the other. The pair is entangled, so they have become one system. So if you measure A, you measure B also. So what Einstein did was, they assumed that measurement of A here, anything measurement we done on A does not affect any measurement of B. And Bohr disagrees. He said that since the state is entangled, now he is using Schrodinger word language. Since the state is entangled, you measure A. When you measure A, you measure B. So this is his defense. This is a very beautiful defense. But there is a problem. The problem is, if the two particles very far apart, how does A knows that measurement is being done on B? That means anything done on A is instantly felt by B. Okay, so this is what, again, Einstein did not like this. This is what he called action at a distance, but he used an adjective, spooky distance, action at a distance. So when Bohr says that the particles are entangled, therefore any measurement, and therefore you measure A, you measure B also, he assumed that something like this happens. He has to accept that principle. Okay. So the debate goes on. The debate goes on. Some believe at that time that an alternative interpretation of quantum mechanics using hidden variables might be possible. Such a theory is known as hidden variable theory. Now we encounter such a variable in thermodynamics and statistical mechanics. Thermodynamics deals with pressure, temperature, internal energy of a gas. Okay? And statistical mechanics, on the other hand, describes pressure, temperature, internal energy of a gas arising from a deeper reality. From a deeper reality, that is the internal motion of the molecules of the gas. So this internal motion of the molecule of the gas is your hidden variable. So at the time it was thought that quantum mechanics can be formulated using such type of variables. But in 1932, John von Neumann proved that a hidden variable interpretation of quantum mechanics is impossible. Mathematically, he proved that such a theory is impossible. And von Neumann was a great mathematician and very, very well respected. So many physicists at that time used or took his words to be true. But 3 years later, a young lady mathematician shows that his proof was wrong. There is some flaws in his argument. But nobody took any interest at that time. Because quantum mechanics was so successful. The only problem with quantum mechanics is that from the very inception, it was so successful. He described so many things. That is his problem. So nobody took this very seriously. Von Neumann formulated, he proved that hidden variable theory is impossible. And the lady mathematicians pointed out the flaws in his argument, and nobody took it seriously. Even then, in 1951-52, David Bohm published a non-local hidden variable theory of quantum mechanics in 1952. And Bell came across this paper in 1952. And he was amazed, he was very surprised that such a hidden variable theory is possible. So he started reading this paper, Bohm's paper, and he finds the same flaw in von Neumann's arguments. Is Grete Hermann. Grete Hermann was the name of the lady professor, mathematician. And Bell found the same flaws in Neumann's argument. So he read this paper seriously, and he studied UPR paper also. And it is said that Bell was sympathetic to Einstein's position. Anyway, so John Stuart Bell came across this paper in 1952. He was fascinated. He started to mull over the problem, studied von Neumann's proof, and found the same flaws in his argument as did Grete Hermann many years ago, about 30 years ago. And he published his celebrated theorem known as Bellman's inequality in a less known journal called Physics, because he submitted his paper to many journals and was refused, wasn't accepted. And for the first time, the debate between Einstein and Bohr was brought down from the metaphysical level to the empirical level, where the debate can be decided on the floor of the laboratory. The debate between Einstein and Bohr was philosophical, metaphysical. Now Bell's theorem brought this debate, this discussion down to the empirical level, when the fate of the debate can be decided on the floor of the laboratory. And in fact, here I give a brief proof of Bell's theorem, but I skip over this. In fact, such experiments have been performed. In each case, it is found that Bell's inequality is violated. So after all, quantum mechanics is correct. Bell's inequality is violated, then quantum mechanics is correct. If Bell's inequality is not violated, obvious, then hidden variable theory is correct. But in all the experiments performed so far, Bell's inequality is violated. So Bohr is correct, quantum mechanics is correct, and therefore our world is not locally real. That is the position. So this is the position as of today. So which is correct, which one is not correct, maybe known after some time, after so many years, But at the moment, the debate is open. Now, to end this, I would like to tell you a weird property of entanglement. And I have proved the mathematical, I have supplied the mathematical proof in my note also, but I don't have any time for those calculations. But I shall briefly tell you the result. There is a weird property of entanglement. Say we took two systems, particle A, particle B, and combine it into a composite system. Then how do we write down the wave function or the state vector of this composite system? So usually what we do is many ways. They use with psi, and some people work with rho, the density operator. So usually what we do is, the state space of A, we call it SA, and you take the state space of B, let us call it SB. Then the state space of SA and SB, A is SA and that of B is SB. Then what is the space of the combined composite system? And usually we take the tensor product of SA and SB. We call it tensor product. You must have come across tensor product when you study angular momentum. Anyway, you take this tensor product, then any vector in this, any combination of the vector in of this space. No, it's wrong. This space is there. Once you know the construct this space means you know the basis vectors. So any combination of these basis vectors will give you the state of the composite system. So you take the linear combination of these state vectors, and that gives you the state of the combined system. But any linear combination of the basis vectors will not be an entangled state, may not be an entangled system. But somehow you are able to construct an entangled wave function or say state. Okay, you know it. I tell you, any linear combination of the basis vectors of this state will not be an entangled state, but some will be. Now, suppose we find the entangled state, or let us say entangled wave function. Now, we use this wave function to calculate, say, the spin of particle B, the expectation value of the spin of particle B, and expectation value of the spin of particle A. It can be done, right? So it is found that the expectation value of the spin of A is 0, and the expectation value of the spin of B is also 0. If the wave function is an entangled one. And so what does it mean? The expectation value of spin is 0. This is 0, this side is 0. What does it mean? It means that the determination of the spin of particle A and the determination of the spin of particle B is uncertain. It is not certain. It may be anything. But in quantum mechanics, as Professor Amuba has just said, all the information of the system are encoded in the wave function. Everything knowable is there encoded in the wave function. But when you use the entangled wave state, the result is uncertain. We don't know anything about it. So this is awareness of entanglement which so disturbs Einstein. Now the situation is can be very beautifully summed up in the words of Shakespeare. And Hamlet says, Hamlet, you know Hamlet drama? Have you read Shakespeare's Hamlet? Ah, good, very good. In this drama, Hamlet says to his friend Horatio, there are more things in heaven and earth, Horatio, than are dreamed of in your philosophy. So with this word, let me conclude my talk. Okay, thank you very much. Okay, just không có chắc chắn tại.
This paper file is with us. Somehow, if you give your email or I will again and again at home. So it is a very good paper, and preparation is around
10 pages.
10 pages. So it is with me. So I should have distributed it. I collected long time back, but we didn't do that one.
Oh, before I conclude, there is recently I purchased a book by Susskind. You know Susskind? Leonard Susskind? He is one of the creators of string theory. Okay, so he wrote a textbook on quantum mechanics. And there, he dwelt about three chapters on entanglement. You must read that if you are interested in this topic. And beautifully written, very accessible also. I bought this at the Impal book fair last year. And there is also one book. Again, I bought it at the Impal airport, the quantum theory. And there are two articles only. There are two articles only in that book. One is written by Max Planck, and the other is written by Niels Bohr. And there you find why Max Planck came to his quantum hypothesis. And Bohr explained why does he come to his model. So you read that very cheap. It cost me only 200 rupees. Very burning here. It is very, very good book. Madhuda loy yaw re. Karigi kumai na ma quantum hypothesis puthore no loy yaw re. Adigi Bohr na shu kumai tau ta ma gi atomic model puthore no loy yaw. Hasana. And about 110 pages. Rupasani dam pi bani.
A few questions we will allow because it is very interesting from the student. One by one.
Philosophical way bani na ko kaim khangam moroi. This is very philosophical.
I'm giving these two books. It is for laymen without mathematics. But one is Einstein and the Revolution, Quantum Revolution by Alan Turing. Alan Turing is the one who got the Nobel Prize for the Bell's inequality experiment.
Alan Turing, Cloud.
Equality Institute. Okay. He wrote this book in 2024 after Nobel Prize because during Nobel Prize he used to give a lot of press interview. So he thought that I will write a book collecting all these small things. So it is very good, but you have to buy. Another is what is real. That again he's trying to define what is real. But he is physics, but a journalist. Alan Becker. He wrote this book, What is Real? The Unfinished Quest for Meaning of Quantum Physics. So it is for, without mathematics, just for laymen and all that. I think, so I don't have this book, but I collected from someone. So if you have any question, please. So his name is Nilakas Sorokhayum, is Inspired Fellow at Teachspo University, did PhD from Tata Institute of Fundamental Research, and he had two postdocs. One is Iser and another is Aisarai. Okay, now
I just wanted to add a comment. Okay, so thank you, Professor Zekendra, for the historical perspective on the quantum. Especially for students, you might think that quantum. I'll just add one comment. Okay? So you might think that entanglement is a very polite. There are wave functions. So the problem is that entanglement is everywhere. When I'm talking to you, actually your wave function and my function is entangled. But the problem, with this new quantum computing, okay, I'm trying to connect with the present, present development. Okay, Professor Zekendra has given the historical perspective. Okay, the problem is about how to control entanglement. Entanglement is everywhere. It's like the iron ore, it's like the oil. Okay, unless we are able to control it, we will not be able to use it, right? So the current, revolution, quantum revolution about quantum computing, quantum information is about how to precisely control the quantum entanglement.
Now, let me just one it. Anything, any interaction, as I told you earlier, manually took entanglement. So then how do you test for any entanglement? You measure B, you measure A. If there is any correlation between these two measurements, the system is entangled. If there is no correlation, no.
I avoid entanglement rule myself.
Oh, yeah. So this is
To make peace in the family.
no correlation.
This is our presentation framework. So now let us have lunch very fast, lunch packet, and let us try to start in the next session. We 3 people are speaking. Professor Rajmohan, Professor Dorindra, and our Subhash Chandra. Okay, please have lunch very fast.